Alright, so clearly this video covers strategies for finding limits. We're only going to go over the basic ones. There are a lot of ways to find limits, but you won't need the super advanced ways in like pre-calc math team, and even for like BC Calc you don't need a lot of advanced ones. So we'll just start with doing practice questions. And just so you know, I didn't make these questions, they're not mine. This kid who just graduated from our school made these questions, so if you're watching this and you made these questions, thank you so much. Alright, so whenever you're doing a limit problem, you always want to start with using direct substitution, just to see, what happens when you plug this number in. So for example, and this right here, this is going to be an example of direct substitution. I guess all of them, we're going to start with direct substitution. That's going to be our first step. And then, depending on what we get when we use direct substitution, then we'll take other steps. And, I'll show that when we get there. So, for this first one, let's try using direct substitution. We have the limit. Let's zoom in here. The first question is the limit as x approaches 2 of x squared plus 4 over x to the third minus 4. What happens when you use direct substitution, step 1, and just plug in 2? We get 2 squared plus 4 over 2 to the third minus 4. And that's 8 over 4, which is 2. Easy, there's nothing wrong with this fraction. There's no indeterminate forms or anything, so the answer to this limit is just 2. Alright, let's try another question. And again, we're going to start with direct substitution. What is the limit as x approaches 2 of x squared plus 4 over x to the third minus 8. And if you notice, we're starting to see a little problem in our denominator over here because 2 to the third is 8, and so we end up with 8 over 0. Now, anything over 0 can't exist. It's undefined. So, what this tells us is whenever we have some number over 0, any number over 0, it probably means there's some unbounded behavior, meaning an asymptote, usually of some sort. And a lot of times they'll tell you graph it in a math class, but if you're competing and you can't have a calculator, you can't really graph it. So you want to think about this conceptually. Now, as 2, let's think about this. As 2 is approaching from the left, the top is still going to be approaching 8. We're just going to be approaching 8 from the left, but it's still going to be 7.99999. So practically 8. And either way, it's going to be positive. So we can just do a little bit less than 8. It'll just be approaching 8 from the left. But the bottom, if you think about this, whenever we're approaching 2 from the left side, that's not really 2. That's 1.9999999 forever, right? And so if we were to take a little bit less than 2 and cube it, that would be a little bit less than 8. So 7.999, right? If we were to just cube this right here, but it was a little less than 2 and not actually 2. So then we said when you subtract 8, it'll be not 0 because this right here is just a little bit smaller than 8. We're subtracting 8 and we're getting a really small negative number. Really small negative number. So if we have some 8, remember this is really an 8, 8 divided by some really small negative number, well that's just gonna go towards negative infinity because we're taking 8 and we're dividing it by negative 0, 0, 0, 0, on and on, 1, which is gonna give us a really, really, really big, honestly infinitely large number because we're getting infinitely close to 8. So the denominator is getting infinitely small, and you get the idea, it's becoming negative infinity. Now on the flip side, if we have x approaching 2 from the right, the top is still 8, it's still positive. Again, the difference in these numbers doesn't really matter unless it's a huge negative positive difference because of the nature of these limits. But from the bottom, now 2 to the third is a little bit over 8. So 8.00001 or something. So when we subtract 8, it's a really small positive number. And so we know that when we divide 8 by something really, really small, it's going to approach infinity. And since it's positive, it's going to be approaching positive infinity. So one way to think about this is if n is equal to 0, it's unbounded behavior, and you need to think about the graph. All right, so what happens if when you plug in your number, you don't get a number over 0? What if you get, I don't know, just, hypothetically, not like we're going to get this in the next question or anything, but what if you got 0 over 0? Let's try this question randomly where we don't know what's going to happen when we plug in 2. We have x squared minus 4 over x to the third minus 8. Remember, first we always want to do direct substitution. I know you probably see how you can factor this, but first we want to just plug it in because that's technically how you're supposed to do it. And this becomes 2 squared minus 4 over 2 to the third minus 8. And we can see that this is 0 over 0, which is an indeterminate form. Now, if it's 0 over 0, that's telling us that there's probably a hole in here, a removable discontinuity. I mean, not necessarily, but there could be, and looking at our numbers, there could be one at 2, right? Because it's 0 over 0. And so how we would get rid of that is factoring. Because all we're essentially doing is, like, let's say we have a function and it has a removable discontinuity at 2. So obviously we're getting an indeterminate form at 2 because there's nothing that exists there. But we don't care what the function is at 2. There could be a hole. We don't care. We just care about what the function is approaching as the x-coordinate approaches 2. So if that hole weren't there, what would it be approaching? And we find that by factoring and getting rid of the hole. So this is the limit as x approaches 2 of x plus 2 times x minus 2. That's a difference of squares. And on the bottom, we have a difference of cubes, which is x minus 2, x squared plus 2x plus 4. And so we can cancel out this little thing. This was causing all of our problems, this hole right here. And we're left with, so x plus 2 over x squared plus 2x plus 4. Now let's try direct substitution, and we get 2 plus 2 over 2 squared plus 2 times 2 plus 4. So that's 4 over 12, which is 1/3. And that is our limit. And so sometimes if it's 0 over 0, that you can try factoring. One of the strategies is factoring. All right, let's do a different problem. Limit as theta this time approaches 0 of sine of theta over sine of 2 theta. This is a pretty common example. You'll see this often. So when you try direct substitution, you get sine of 0 is 0 over sine of 2 times 0 is also 0, and that doesn't work. We can't really factor this, but we do know our trig identities. So we can turn this into limit as theta approaches 0 of sine of, I don't know why I put an equal sign there, of sine of theta divided by 2 sine theta cosine theta. Wow, the sign on the top and bottom cancels out, and we're left with the limit as theta approaches 0 of 1 over 2 cosine theta. Cosine of 0, because now we can use direct substitution, is just 1. So this is 1 over 2 times 1, which is just 1/2. And that would be the answer to this limit. So another thing we can do if we get 0 over 0 is use trig identities. And again, this is exactly what it says on Khan Academy. So if you want some practice, always go to Khan. Or look at some of the theta tests. Plug in. All right, let's do another example of a strategy. So, and again, x as x approaches 2 again. As x approaches 2 of x minus 2 over 1 minus 3x, square root of 3x minus 5. Okay, by this point we probably know, I don't think direct substitution is going to work. I don't care. We're going to try it anyways. So this is 2 minus 2 over 1 minus the square root of 6 minus 5. Oh, who could have guessed it's 0 over 0? That's indeterminate. We need to find another way to solve this. And now we're going to be using conjugates. These aren't complex conjugates, radical conjugates. We have a problem with the denominator. Like, it's fine if the numerator is 0. The denominator just cannot be 0. So if you see like radicals or complex numbers, Lots of times the problem will involve just using the conjugate, so even if you really don't think it'll work, just try it. So what this involves is we know that this is 1 minus the square root of 3x minus 5. We want to multiply it by 1, but we're not going to just write like 1 over 1. We're going to write 1 plus 3 square root of 3x minus 5 over 1 plus the square root of 3x minus 5. This is its radical conjugate. And so now this becomes x minus 2. Oh, I should probably have the limit thing here. X approaches 2. X minus 2 times 1 plus the square root of 3x minus 5. And I cannot stress this enough. Do not expand this out. Leave it like this because odds are the bottom is going to cancel. So now we have 1 minus the square root of 3x minus 5 times 1 plus the square root of 3x minus 5. Jeez, I'm so tired of saying the square root of 3x minus 5. This is a difference of squares, right? That's why we multiplied it by the conjugate. So the denominator is going to end up being 1 squared minus 3x minus 5 and the square root squared. So that's just 1 minus 3x minus 5, which is 6 minus 3x. Now, would you look at that? 6 minus 3x is equal to negative 3 times x minus 2. And on top of that, wow, we have x minus 2. 1 plus square root 3x minus 5. Cool, this is gone. That's what was creating our problems by giving us the 0 over 0. So now we can just use direct substitution. When we plug this in, we get 1 plus the square root of 3 times 2 minus 5 over negative 3. So that is 1 plus 1 over 3, which is negative 2/3. So that's one more strategy. Use conjugates. All right, but what if it's a limit to infinity? Because these have all been limits to a certain value, right? A point. But if it's a limit to infinity, well, like there's not going to be a hole at a limit to infinity. Although you might get a few other indeterminate forms, and so you need to know how to be able to solve a limit to infinity. Well, let's look at this example right here. As x goes to infinity, you have 2x to the third minus 4 plus sine x over x to the third plus 2x squared minus 8. Okay, so in this case, you kind of want to think along the lines of horizontal asymptotes. Now, in the face of this 2x to the third, this x to the third term, the negative 4, and especially the sine x, are really insignificant. They're not going to change the overall value of this ratio, right? Because that's all a fraction is, essentially a ratio. Too much. The only thing that really matters here is the x to the third term because it's the biggest term by far. It's the most significant. Nothing else really impacts this. So if you remember back in Algebra 2 when you learned about horizontal asymptotes, all this is really asking is the end behavior of the function as x approaches infinity is literally just the end behavior of the function, which is the horizontal asymptote. Is there a horizontal asymptote here? Yes. Since the highest term, the ratio of those coefficients, that's equal to 2 over 1, which is just 2. The horizontal asymptote is going to be at y equals 2, right? That's an Algebra 2 scale. So, that would be the limit as x approaches infinity. It's the horizontal asymptote of y equals 2. And this is just, you have to understand that this grows so much faster than the rest of the terms. Another way you'll commonly see people describe it is like the biggest term is x to the third. So if you were to divide both the numerator and denominator by x to the third everywhere, you'd get 2 minus 4 over x to the third plus sine of x over x to the third divided by 1 plus 2x squared over x to the third, which is just becomes 2 over x, minus 8 over x to the third, limit as x approaches infinity. So if you notice, as x approaches infinity, all of these numbers that are fractions are going to get like infinitely smaller. They're going to approach zero. They're going to get closer and closer and closer to zero, and our limit itself is going to get closer and closer and closer to 2 over 1, which again is y equals 2. Let's do another example. What about the limit as x approaches infinity of natural log of x plus x over x? The first thing I'm kind of thinking of doing when I see this is I split this into 2 different terms, just because this is a pretty simple fraction, and it gives us natural log of x over x plus 1. Now, this also involves thinking about how fast is one function growing to another. And there's a general rule for this. You always want to think about the fact that for any like number n, and just x is going to be x, like how we usually use x in a function like an input, any number like 2 to the x or something, 3 to the x, 4 to the x, any number or just any number to the x is always going to grow faster than x to a number. It's just always going to grow faster than log base a number to x. So like, for example, if we had this, n to the x would grow like 2 to the x grows so fast. X to the n, kind of like a parabola, x squared plus 2x or whatever, that grows at a slower rate. And log of n to the x, that grows even slower. It goes so slowly, right? So this is the kind of hierarchy you want to think of. Speaking of which, this is natural log of x, so log base e of x, that's x to the first. The denominator is going to grow way faster, meaning as x approaches infinity, this is going to be up here somewhere, whereas the log is not going to be even close to that. So this just is like 0 plus 1, because this natural log of x is insignificant compared to this x. So the answer to this question is 1. And so this is really important to note. And for our last question of this video, we're going to do the limit. Actually, let me write this down. Wow. All right. So for limits to infinity. Well, I don't really know how to fit this in, but I guess this is just a separate little thing. You want to look for horizontal asymptotes. You want to consider which grows faster. What grows faster? And we're just about to cover completing the square. So this is really all the basic limit strategies that you will need to use. Remember, just get these down and you'll be fine. All right, so the limit as x approaches negative infinity of x plus x squared plus 2x. Now, a lot of people, when they see this, think, wow, the 2x is insignificant compared to the x squared. This is just x plus the square root of x squared, so it's just 2x. Let me tell you a story about this kid on our team who, all the limits in the regional tests, so many of them could be solved by just plugging in a really big number for infinity. This is one of these questions where you plug in a really big number for infinity, you get the question wrong, and like whenever you assume this 2x is insignificant, it's wrong. Because when you add this radical here, this 2x is not insignificant anymore when we're comparing all of this. What we really want to do here is we want to change this to the limit, of course, as x approaches negative infinity of x plus 1 squared minus 1. Now, if you don't see what I did here, it's okay. This is called completing the square. You do it in algebra 2, pre-calc. It's what we're doing here. It's this. If you think about it, x plus 1 squared is x squared plus 2x plus 1, and you subtract 1. That's the same thing as x squared plus 2x. So we're just taking this middle term, we're dividing it by 2 to get x plus 1 squared, right? Because x plus 1 is half of 2 squared. And then since that gives us x squared plus 2x plus 1, and this inside of this is x squared plus 2x and then nothing, we want to subtract 1. So that's why we subtracted 1, because we just added 1 when we squared this. And now this 1 is really insignificant, as that's going to negative infinity. And so actually first let's pretend it's going to infinity. Let's just pretend. Actually no, I can't do that, sorry. That makes the question really weird. And so now we can really just take the square root of this whole thing squared when this 1 is really insignificant, and it becomes x plus the negative as square root, because this is as it's going to negative infinity, negative x plus 1. So we took the square root of x plus 1 squared, and it's got to be the negative square root because this is as x goes to negative infinity. And so this becomes x minus 1, which is equal to negative 1 as our answer. And that is completing the square. And wow, that was a lot of talking, but you know, at least you learned some pretty, wow, important stuff.